Our next talk is by Yifan, Fuzzing Guided by Bayesian Program Analysis.
Okay, thank you. Hello, everyone. I'm Yifan Zhang from Peking University. Today, I'm going to talk about our recent work on fuzzing guided by Bayesian program analysis. This is going to work with my advisor, Zhang. Our work is based on large-scale target-guided greybox fuzzing, or LTGF for short. Given a program under test and a large set of targets, usually coming from static analysis alarms, LTGF aims to trigger as many potential new bugs at these targets as possible. LTGF operates in two alternating stages, exploration and exploitation. In the exploration stage, LTGF performs coverage-guided mutation to accumulate more seeds, which enhances its capability to detect bugs during the exploitation stage. In the exploitation stage, LTGF first conducts target prioritization. For those high-priority targets, LTGF carries out directed mutation to trigger the potential bugs associated with them. However, existing approaches for target prioritization lack a systematical design. For instance, they prioritize targets one by one in sequence. This strategy is not only ad hoc, but also cross-grained, causing LTGF waste a significant amount of time on targets that are unlikely to contain bugs. Let me use a simple example to show the limitation of existing LTGF. In this program, we run timed analysis to find potential out-of-bounds bugs. The variable A comes from the input, and depending on its value, the running goes into one of three branches. The variable A is also input controlled, so it's tainted, and any variable derived from A is tainted as well, including B and C. Since A, B, C are all used as error indices, the analysis raises three alarms, A1, A2, and A3. We also assume there are other alarms from the analysis, such as A4, A5, and A6. Now, suppose we start with just one seed, E equals 0, A equals 0. Existing LTGF first runs at an exploration stage, where the goal is to maximize coverage. Let's assume this stage successfully covers all three branches for A equals 0, 1, 2. For each coverage pattern, the fuzzer only keeps one seed. So at this point, our seed set is E equals 0, A equals 0, E equals 1, A equals 1, and E equals 2, A equals 0. Next, LTGF runs exploitation fuzzing for each target one by one. For A1, LTGF picks the seed that is closest to that target, say A equals 0, A equals 0, and mutates it for a given time. Assume 1,000 mutations in this time budget. The bug behind A1 is triggered whenever A mode 100 equals 0. So it's quite likely that one of those 1,000 mutations will hit such a value and expose the bug. Then LTGF moves on to A2. This bug only occurs when A is exactly 100. With 1,000 random mutations, the chance of hitting exactly 100 is extremely low. So it's very unlikely we will trigger this bug. For A3, the situation is even worse. Here C is always odd, so C mode 2 is always 1. This means the corresponding alarm is actually a false positive. No matter how we mutate the seed, we can never trigger a real bug there. So the time spent fuzzing for A2 and A3 is basically wasted. The fuzzer has almost no chance of finding a bug, yet A2 and A3 receive the same time budget as A1. This example shows why we need a more systematic way to allocate fuzzing time, so that we invest more in valuable targets like A1, instead of treating all targets as equally promising. We make the following contributions to address this problem. First, we systematically formulate it as the reachable fuzzing targets problem. To solve this problem, we then redefine the semantics of Bayesian program analysis to enable accurate prediction of target reachability and effective generalization from fuzzer feedback. Building on this foundation, we propose Fuzzer, a framework that leverages Bayesian program analysis to provide semantics-aware, fine-grained, and adaptive fuzzing guidance. Finally, we demonstrate the effectiveness of Fuzzer on real-world programs. showing superior bug detection performance compared with baseline approaches. Next, we first introduce the reachable fuzzing target problem, then present how our redefined semantics Bayesian program analysis enables semantics-aware fine-grained and adaptive guidance for LTGF, and finally describe our experimental evaluation. We first define the reachable fuzzing target problem. The entire LTGF process can be formalized as the following loop. First, acceleration fuzzing is performed to continuously expand coverage and obtain the current seed set S. Then, several rounds of exploitation fuzzing are conducted based on S. In each round, target prioritization is used to select a target T, and exploitation fuzzing is performed with the goal of triggering bugs at target T. After several rounds, the process returns to acceleration fuzzing. We define a target T as reachable if and only if, in a single round of exploitation fuzzing within a given time budget based on the current seed set S, there is a probability of at least A of generating an input that triggers T. In practice, we set A to 99%. Therefore, our problem becomes predicting for each target T the probability that T is reachable. Taking the above example, suppose our current seed set is E equals 0, A equals 0, E equals 1, A equals 0, and E equals 2, A equals 0. For the three targets A1, A2, and A3, A1 is a reachable target because within given time budget, that is 1,000 mutations, the probability of triggering the bug is at least 99%. A2 is not a reachable target because the probability of triggering the bug within 1,000 mutations is below 1%. A3 is also not a reachable target because the bug can never be triggered, regardless of how we mutate the seeds. Thus, we successfully reduce the problem to predicting for each target whether it is reachable. By prioritizing those targets that are reachable, we can effectively address the limitations of existing LTGF and improve its efficiency. We propose a framework called Bayesian, which uses Bayesian program analysis with redefined semantics to predict the reachable fuzzing targets problem, thereby guiding LTGF. Its workflow is as follows. Building on the LTGF workflow, we use the redefined Bayesian network semantics to compute for each target the probability that it is reachable by exploitation fuzzing given the current seed set S. We then perform exploitation fuzzing on the target with the highest predict reachability probability. The result of this exploitation fuzzing is fed back into Bayesian network. If the target bug is successfully triggered, we provide positive feedback. Otherwise, we provide negative feedback. Finally, as each round of exploration fuzzing completes and the seed set expands, some targets that were previously unreachable may become reachable. Therefore, we clear all accumulated negative feedback after each exploration stage to ensure more accurate probability estimation. We first illustrate the original semantics Bayesian program analysis with an example. In the code fragment, variable A is read from external input, variable B is derived from A, and variables C and D are derived from B. Finally, C and D are used as error indices. We apply taint analysis to detect potential out-of-bounds bugs in these statements. We use taint V to denote that variable V is tainted by external input, and alarm A to denote that alarm A holds. Initially, we have taint A. According to taint propagation rules, we can derive taint B and further taint C together with alarm A1 when C is used as an error index. Similarly, we obtain taint D and alarm A2. We call this directed graph as a derivation graph. Each derived tuple represents a program property produced by the static analysis. We then transform this derivation graph into a Bayesian network. Each derived tuple is modeled as a Bernoulli variable, indicating whether there exists some input under which the corresponding program property holds. Conditional probabilities between variables are defined according to the graph structure. For brevity, we set such probability to 0.8. Using this Bayesian network, we can compute the probability distribution of each variable given posterior information. For example, we obtain that both A1 and A2 have a reachability probability of 0.512. Suppose there are other alarm statements in other parts of the program, but with lower probabilities. If the user inspects A1 and confirms that it is a real bug, we can treat this positive feedback as posterior evidence and recompute the probabilities. Since alarm A2 is connected to alarm A1 in the Bayesian network, the probability of A2 increases. However, the semantics of existing Bayesian program analysis is defined over all possible program inputs, whereas the inputs that a fuzzer can actually generate form only a subset of this. Therefore, we need to redefine the semantics to adapt Bayesian program analysis to the fuzzer setting. We redefine the semantics of each Bernoulli variable to express whether or not it is reachable by exploitation fuzzing under this new semantics. But the Bayesian network computes for each alarm the probability that it is reachable, which can be directly used to predict the reachable fuzzing targets problem. Furthermore, the outcome of each exploitation fuzzing attempt precisely indicates whether a given target is reachable under the current setting. So we can treat this further feedback as posterior evidence and recompute more accurate probability estimates. Next, we show how Bayesian program analysis with the redefined semantics can provide semantics-aware and fine-grained guidance for LTGF. In this example, the key insight is that A1 and A2 share the same root cause and are both reachable by exploitation fuzzing. That is, there is at least a 99% probability of generating inputs that trigger them. We use the positive feedback obtained from exploitation fuzzing on A1 to increase the reachability probability of A2, thereby achieving precise prioritization of alarms that share the same root causes. We will show how our approach works. The fuzzer will first select A1, which has the highest ranking, as the next target. According to the triggering condition, the probability is around 100th. So the fuzzer can quickly trigger this bug through rapid mutations and provide positive feedback to the Bayesian network. Based on this posterior information, a new probability distribution is recalculated. Since alarm A2 is connected to A1 in the network, its probability increases, making A2 the next target. The triggering probability for A2 is approximately 1/200th. So the fuzzer can also quickly trigger A2 through multiple mutations. We present a second example. For easier understanding, we make a small modification to the first one. Now variable B must be an odd number, so C and D are also always odd. As a result, A1 and A2 can never be triggered, since both C mode 4 and D mode 8 will always be greater than 0. The taint analysis produces a derivation graph with the same structure as in the previous example. However, because it does not consider precise value ranges, it over-approximates and incorrectly reports the false alarms A1 and A2. The key insight is that A1 and A2 are derived from the same over-approximation and are both unreachable by exploitation fuzzing. That is, there is a 0 probability of generating inputs that trigger them. We use the negative feedback obtained from exploitation fuzzing on A1 to decrease the reachability probability of A2, thereby accurately lowering the prioritization of alarms arising from the same over-approximation. We will now show how our approach works. The fuzzer will target A1 first because it has the highest probability. After some time mutating inputs, the fuzzer realizes the bug cannot be triggered and provides a negative feedback. Since alarm A2 is connected to alarm A1 in the network, the probability of A2 also decreases. This allows the fuzzer to skip this false alarm and focus on other potentially triggerable targets, effectively avoiding wasted time. Next, we look at a third example. Building on the previous two, this one introduces a new variable E. The value of E is set to 1 only when the external input is a multiple of 1,000. Otherwise, it is 0. If E is 0, then C and D become 0 only when B hits an exact magic value, such as 100 or 200. In that case, they may trigger the bugs at A1 and A2. But if E is 1, we don't need an exact magic value anymore. It's enough for B to be a multiple of 100 or 200 to trigger A1 or A2. The derivation graph from tensor analysis, again, has the same structure as in the previous examples. Here, we show how our approach uses adaptive guidance to help the fuzzer make better decisions at the different stages. At the beginning, the fuzzer has no seeds with A equals 1. At this point, the probability of triggering the bugs at A1 and A2 by random mutation is extremely low because it would require mutating B to an exact magic value. The key insight is that A1 and A2 are both constrained by the same input condition, and under the current seed set, they are both essentially unreachable by exploitation fuzzing. That is, the probability of generating inputs that trigger them is below 1%. We use the negative feedback from exploitation fuzzing on A1 to prioritize such targets that are unreachable under the current seeds. We will now show how our approach works. The fuzzer will first target A1. After attempting mutations for well and failing to trigger the bug, it gives negative feedback to the Bayesian network. Since alarm A2 is connected to alarm A1 in the network, the probability for A2 also decreases. Thus, the fuzzer can skip the currently unreachable alarm A2 and focus on other potentially reachable targets, avoiding wasted time. After another round of exploration fuzzing, the fuzzer has accumulated more seeds and now has seeds with E equals 1. At this point, we clear all previous negative feedback. The insight is that with the new seed, the input constraint statement is overcome, and both A1 and A2 become reachable by exploitation fuzzing. That is, there is at least a 99% probability of generating inputs that trigger them. By applying negative feedback elimination and use the updated result of exploitation fuzzing on A1, we prioritize targets that become reachable again. We will show how our approach works. The alarm with the highest probability is still A1. The fuzzer will again target A1. According to the new triggering condition, the probability is about 1/100. So the bug can be triggered through mutation in a short time. The fuzzer then gives positive feedback to the Bayesian network. Since alarm A2 is connected to alarm A1 in the network, its probability increases, making A2 the next target. The triggering probability for A2 is approximately 1/200, so it can also be triggered in a short amount of time. We conducted experiments to evaluate the effectiveness of our approach. We built Bayesian on top of the LTGF2 fish fuzz and use a tensor analysis based on SVF. We compare our approach with the following baselines. The first one is prospector, the SOTA in LTGF. The second one is fish fuzz, the foundational fuzzer of our approach. The third one is fun fuzz, the SOTA of coverage-guided greybox fuzzing based on non-Bayesian lightweight static analysis. We include the fun fuzz to demonstrate that Bayesian program analysis provides stronger guidance for fuzzing than conventional static analysis. The last one is the AFL++, the foundational fuzzer for all three baselines as well as our approach. We use the same benchmarks as prospector, including 24 real-world programs with various input formats. We also use the same metrics as prospector. We measure the median time to exposure, or TTE for short, across 10 repeated runs. TTE represents the time required to trigger a bug for the first time. Our time limit is 60 hours, and the total experimental time amounts to approximately 9.86 CPU years. We use a Venn diagram to illustrate the bugs discovered by different fuzzers. Compared to other baselines, Bayesian is able to find 3.25 to 13 times more unique bugs, which clearly demonstrates its significantly stronger bug-finding capability. We further use bug discovery curves over time to provide a more direct visualization. As shown, Bayesian does not have a leading advantage in the first 40 hours. However, as a large amount of feedback accumulates, its strong guidance ability becomes apparent in the final 20 hours, clearly surpassing the other baselines. This further demonstrates the effectiveness of Bayesian program analysis in guiding fuzzing. We measure the computational overhead of Bayesian inference. On average, The time spent on Bayesian inference accounts for approximately 0.31% of the total running time. Therefore, the overhead introduced by Bayesian program analysis is tiny and fully acceptable in practice. We conducted application experiments to verify the necessity of removing negative feedback. As time progresses, many bugs become reachable, and if negative feedback is given prematurely, we may lose the opportunity to trigger them. In fact, the configuration without removing negative feedback discovers 16 fewer bugs in the end. Therefore, removing negative feedback can significantly enhance bug finding capability and is highly necessary. Finally, we use Bayesian to test the latest version of software, including the most recent commits for the 24 programs used in our controlled experiments, as well as popular projects with a high number of stars in OSS fuzz. Both groups of software have been extensively fuzzed 24/7, yet we are still able to discover a large number of important new bugs. In total, we found 39 bugs, 30 of which were assigned CVEs. We present some of the bugs we discovered. On the left, we show the 4 most influential bugs, with GitHub repositories have between 7.6 thousand to 26.7 thousand stars. On the right, we show several other high-impact bugs. Overall, our approach demonstrates strong practical value in real-world software engineering. Finally, I will give the conclusion of our work. First, we systematically define the reachable fuzzing targets problem and redefine the Bayesian program analysis semantics to enable accurate prediction of this problem and further feedback generalization. Next, we propose Bayesian, a framework that leverages Bayesian program analysis to provide semantic-aware, fine-grained, and adaptive fuzzing guidance. Then, we extend Bayesian program analysis beyond static alarm ranking to automated fuzzing guidance for bug discovery. Last, we demonstrate the effectiveness of Bayesian on real-world programs, showing superior bug detection performance compared to baselines. And that's all. Thanks for listening.
Questions?
So thank you for the talk. I wanted to know, so how do you determine that it's a bug? Here you were using out-of-bound array indexes, but do you typically do fuzzing? Sorry, I'm a bit unfamiliar with fuzzing. Do you typically do this by comparing against a set of tests and you fuzz the inputs? But how does that typically work?
Sorry, can you speak?
Yeah, sorry. So I'm wondering what kind of bugs can you detect using fuzzing?
What kinds of what?
What kind of bugs? Like just out-of-bound indexes, or?
There are address errors. We use ASAN, address sanitizers, such as heap buffer overflow, out of bounds write read, and null pointer dereference. All about memory errors. Yes.
Thanks.
Okay.
There's no more questions. Maybe we can finish a bit early there and go and see some posters. Thank you very much.
Okay, thank you.